Welcome, everyone. My name is Kai Ji. I am a software engineer working for Intel Ireland. Most of my work in the past few years were focused on Cryptodev development and Intel crypto acceleration hardware QUIC enablement in DPDK. Today, I would like to draw your attention to what we have done on the Asymmetric Crypto Framework in the past few months. Before we started, I would like to thank especially to Eric Christoph and Shimek Zhang. They have significantly contributed to this project. This talk won't be here without their support. Now, without further ado, let's begin. For this meeting's agenda, we want to talk about currently status on the DPDK Asymmetric Cryptodev in 2022, some highlights we did in common asymmetric Cryptodev, API changes, data structure rework, etc. And then we would like to get a discussion about the currently issue in the asymmetric testing and some unit test refactor we have been working on. And what's the future works we're planning for the asymmetric Cryptodev in DPDK. Unfortunately, most of the topic covered in this talk are based on the code walkthrough, so I do want to apologize in advance for no fancy diagram here for my slides. Okay, now, what have emerged in DPDK 22.07 release? We have about 30 patches have been accepted related to asymmetrical crypto development since beginning of 2022. Among those 30 patches, 17 of them are asymmetric Cryptodev changes on common data structures and APIs. At this moment, we also have about 13 patches related to asymmetric crypto in the patchwork backlogs. Most of them are in V1 or V2 state. Now let's go to some highlights changes in 2022. So first, as asymmetric crypto key exchange operation type. Originally, the key exchange type enum are defined in the asymmetric op type enum, alongside with op encryption, op decryption, op sign, and op verify. Actually, the use case of this key exchange operation, like private key exchange, private key generation, public key generation, are unrelated to those asymmetric operations. Therefore, we separate the asymmetric key exchange type from the op type enum to make it clear and more readable. In the PMD capability, op type bitmask, both op type enum and the key E type enum are supported and not conflicted. For example, in RSA, the op type can be set to sign, verify, encrypt, decrypt. In DH, the op type can be set to KE type, for example, like private key generation, public key generation, or shared secret compute. The second changes, based on the previous changes, we move out the DH key exchange operation type from X-form structure to DH op parameter structure. The DH key op now are dereferenced from the RTE crypto op instead of asymmetric session pointer. The reason behind this is a single X form session should be well enough to perform both DH operations. For example, in the shared secret compute, a pair public key need to be generated. So you will be assigned this to public key generation plus shared key compute. If KE type still in the X form numbers, a session will have to be created twice for this same group of operations. It also help to DH to extend to support elliptic curves as well. We also add a new elliptic curve Diffie-Hellman parameter structure, which called the crypto ECDH op parameters. Inside of these parameters, we include the KE type, which I just described before, private key, public key, and shared secret. Private key is unsigned big integer in big Indian format. It is output pointer as public key if the KE type is private key generate. Its input private key, where its KE type is one of public key generate or shared secret compute. In case of a private key length is 0 and KE type is set to public key generate, a random generator capability device will need generating a public key. We'll need to generating private key to use it for public key generations. A public key pointer basically is type of crypto EC point structure. It's made by RTE crypto primes. X and Y represent as X coordinate and Y coordinate used for the eclipse curves. It's output pointer to a public key where a KE type is public key generates, and it will be input for pairs public keys when KE type is share secret computes. Like a public key, the share secret basically is output point to calculate the shared secret when KE type is share secret computes. We have added a new padding flag in asymmetric op structure. Diffie-Hellman padding is used in certain protocols. By default, the public key and share secret will be padded into the left with 0 to the size of defined hash algorithm. Even same protocol might be used in different approach. For example, in TLS 1.2 or 1.3, they have different padding configurations. If this flag is set, the public key will be returned without a leading 0 byte. And if this flag is not set, a public key will be padded to the left with 0 to the size of underlying algorithm. And this is the same behaviors for the share secret as well. We also clarify the usage of RSA paddings. As more padding configuration members added into a padding, therefore having a separate structure for padding parameters will make more sense. However, this padding structure is still located inside of RSA op prime structures. Supported RSA padding hash algorithm are MD5, SHA-1, SHA-2, SHA-384, SHA-512. There's a number of padding styles. In PKCS15, it's only used for RSA signing operation. This field is used to determining value of the digest info structure. Therefore, specifying which padding algorithm is used to creating a message digest. For encryption or decryption, this field is ignored. And OAEP and the PSS inside of this padding will need to be specified which hash algorithm is used for padding scheme. We added MGF1 hash is for mask generations for PSS padding and OAEP padding. Also, the SOP length and the OAEP labels is common parameters to PSS and OAEP paddings for RSA. One thing is worth to mention when RSA padding none and the asymmetric op verify selected, the cipher pointer in RSA op parameter structure should be output to be stored for signature decryption without padding. This has never been, it's been worth to mention there. Okay, so what was the problems in asymmetrical crypto unit test app? What we're facing? So currently there are 5 unit test suite supported in DPDK test, OpenSSL, QUIC, CN10K, etc. So by nature of the asymmetric, it's very complex. We have covered a lot of different scenarios. Test scenarios need to cover different variation of operation time, such as encrypt, decrypt, sign, verify, private key generating, public key generating, shared secret computes, not to mention in different modeling size, key size, padding configuration, etc., etc. So we also need to have some flexible configuration parameters so we can configure those options easily. It's good to have some reference results so that we could compare the PMD result with the correct result so that we know PMD is functioning correctly. And then we should have less maintain effort. All of those are currently missing. So we are introduce ultimate unit test framework refactor. So with all the problems in mind, we create ATS rule structure to capture the asymmetric parameters that need to be executed. The rule contains a configuration of the key size, op mode, padding configurations, mod length size based on the test algorithm. And also we are using random number generator for input plain data generations for another required data if needed. Also, once we have a rule created, input data generated, and we are using OpenSSL to perform same op and to generating exact result and stored into input data result pointer. A typical op function call flow can be once the test op function calling compatibility check to the PMD to see compatibilities supported. Then we prepare asymmetric transform session, create a session calling incube burst, decube burst. Then we can compare the result in the end. So this slide is showing an example of RSA unit test structures. Inside of RSA vector structures, we have X form type. They're just E values. This is just a snapshot. The actual content, it will be much more bigger. It will contain sign values, D, P, Q value for all the asymmetric usage for RSA. And on the right-hand side, we have RSA rule configurations. Inside of the rules, we will have, in this case, we will have key size 1024. RSA key types will be exponential, padding configurations none, plain data length 128, and this operation will be RSA encrypt and decrypt. Once everything has been set up and we feed into OpenSSL engine, we're taking leverage of the OpenSSL PMD, and you see exactly same function call but built into this automation test. We're calling RSA public encrypt or RSA private decrypt or private encrypt to perform whatever the rule has been configured. One of test example results will be looks like this. So it will be have similar styles of the current DPDK unit test. It will be dump out all the generation data has been generated by random generators and execute all the rules test. So on the right, you can see it will be this test will be generating RSA key into exponential keys or quadruple format. And once all passed, it will be generating a nice result to showing exactly the same what happening here. Okay, that's pretty much what I want to address for this talk. For next step, we have EC point verify function need to be merged for Cryptodev. For QUIC, Intel QUIC accelerator engine, we have ECDH currently ongoing. We want to materialize the ECDH. For the asymmetric unit test refactor, we are currently supporting RSA. We're planning to get a DH or DSA integrated before for this 22.07 release. The previous OpenSSL are implemented based on 1.1x library, so we also want to support for 3.0 library in the future. And we're also seeking for opportunity to do a crypto API sample code showcase for this asymmetric unit test refactor. Of course, this work cannot be done alone, so I would like to thank you for Kira Power, Brian Donnelly for code reviews, John McMara for project management, Fiona or Maxim for QUIC support. Okay, that's all from here. Thank you very much. Any questions?
Do we have any questions from our in-house audience at all? Any questions for Zhikai? Okay. Any questions at all? No? Okay. Zhi, thank you so much for taking the time to talk to us today and presenting your work. Really appreciate your input, and it's great to hear about what you're doing. So thank you. We have a round of applause for Zhi.